Let's find the equation of the tangent plane to the function f of x equals 3 times the quantity x minus 1 squared plus 2 times the quantity y plus 3 squared plus 107 at the point P, which is 2, negative 2, 112. Well, the first thing I'm going to do is I'm going to look for my partials because I know that this is going to have the form z minus z naught equals the partial with respect to x, x minus x naught, plus the partial with respect to y times y minus y naught. So I need to find these two partials right away. So the partial with respect to x is going to be 6 times x minus 1. And I need to evaluate that when x equals 2, y equals negative 2. So I'm going to evaluate this at the point 2, negative 2, which is easy because there are no y's. So 2 minus 1 is 2. So this is just 6, or 2 minus 1 is 1. So 1 times 6 is 6. So this partial is just actually equal to 6. Now the partial with respect to y is going to be, well, this is going to be 0. So this is going to be 4 times y plus 3 to the first. And again, I need to evaluate this at the point 2, negative 2. There are no x's left in here. So at negative 2, I still get 1 in here. So 4 times 1 is 4. So the partial with respect to y is just going to be 4. Therefore, the equation of the tangent plane at very specifically the point 2, negative 2, 112 is z minus z naught, well, z naught is 112, equals a partial of x, which is 6 times x minus x naught, well, that's x minus 2, plus the partial with respect to y, which is 4 times y minus y naught, which is minus minus 2, so that's plus 2. And there's the equation of the plane. Now, I'm going to end up plotting this in Maple, so it may be a little bit easier to write this as z equals this function. So I'm going to write this as z equals 6 times x minus 2 plus 4 times y plus 2 plus 112. Now, before I graph this, I want to repeat this using a vector approach. Now, I know my normal vector is going to be 6, 4, negative 1. So all I need to do now is find the dot product. So I need 6, 4, negative 1. Man, that looks like a 7. And I need to dot this with x minus x naught. So that is x minus, where is it, 2. Y plus 2. Z minus 112. Of course, that equals 0. And when I do, I get 6 times x minus 2 plus 4 times y plus 2 minus z minus 112 equals 0, which, solving this for z, I'm going to distribute this negative, and I will get z equals 6 times x minus 2 plus 4 times y plus 2 plus 112, which is exactly the same thing as I got up here. So let's take a look at this in Maple and see what it looks like. So here's, I'm going to set up the with plots, and I need the student and the vector calculus. You see, this is my original plane, the top one. This one, that's my tangent plane. And of course, I went ahead and drew the position vector to the point 2, negative 2, 12. Because if this works out well, then I'm going to see the original function, the tangent plane, and the arrow pointing to the point of intersection between the tangent plane and that original function. So let me see, we'll display it. It looks like I missed here, so let's, yeah, there we go, I missed the A. There we are. So let's go ahead and make this a little bit bigger. And here is obviously my original function. And then this looks like a plane, so let's spin this around a little bit and see what's going on. And lo and behold, just like we knew what we were doing, right here is that position vector. And I think it's probably not too hard to convince ourselves that this position vector is going right where it should be going, to the point where this curve, or this surface, is actually intersecting that tangent plane. We can spin this around a couple different directions to convince ourselves that that is a reasonable thing. And the cool part about this is, if you take a look at the process that I followed to actually find it, there are a couple of different ones. The vector approach is kind of nice because, you know, we've come to love and adore vectors. So making that vector approach is very quick and easy. But it doesn't really matter. You're still going to need this partials, and it's just almost just as easy to simply use this form. So really we have multiple options to us in terms of how it is we want to find the equation of that tangent plane. Now, a key thing here, and don't forget, when we find this partial, when we find the partial, we have to evaluate it at x and y. And I put x and y in there, although in this function it didn't make a difference because the partial with respect to x didn't have any y's. And this partial with respect to y didn't have any x's. But that doesn't mean they're all cases going to be like that. So, and actually even the z, that they could, depending on how the function is written, we may have to consider both x, y, and z values to find that partial.